along with Niharika, who could not join because she don't feel well today. So, I mean, most of you are regulars, so I don't need to give a long introduction of IBAC. But yeah, we conduct student talks regularly, so if you ever are interested to give one yourself, please contact us. After the talk, I'll give you some more details about certain groups for the 22-23 batch, because we've already given, but I see I found out that you guys don't know about it. So without any further delay, our speaker is Gourav Kumawat. He's a 5th year physics major. He was a coordinator 2 years ago and he was an advisor last year, and he's an honorary member now. So I welcome him to take the stage. Thank you.
So hello everyone. First of all, thank you for coming. So how many of you are from 22 or 23? Like, because the idea is that some of the slides here initially are about stellar evolution, which was covered in my last talk, but I am just repeating it again so that we all come to the same point. So the last talk was about stars versus stellar objects or fake stars. So no more fake stars. Now we will talk about the real stars. So the content. So we will start with the stellar evolution. Just a basic idea. I will only explain those things which will be relevant for our further discussion. Then we will talk about star clusters. So basically, what is a star cluster and why do we need to study stars in star clusters specifically? Then we will talk about binary star systems, how they evolve and what are their types. And then exotic stellar population, which is the main part, where we will discuss some of the exotic stellar populations which are found in globular cluster. And at the end, I will discuss about my research experience in ARIES. We will be discussing the recent publication and the recent findings. The good news is that the most of this talk is about images. There is hardly any math. But the bad news is that the talk will be long because there are more number of slides. So let's start with stellar evolution. The story of stars. Anyone know what's there in the background? What is this background? Not those people who have attended the previous talks. Not those people who have attended the previous talks. No one?
Merging of two galaxies.
Bro. So this is this is the chart diagram. The periodic table, the Rosetta Stone, constellation. Hertz from Russell diagram. So basically, this is one of the diagrams. There are many different types of diagrams. There is color magnitude diagram, which is basically just an observational version of HR diagram. So HR diagram, you have temperature. You can have temperature. You can have color. Color is basically related to temperature. You don't need to worry about it. And then there are spectral classes as well. The spectral classes are also somewhere related to the temperature. So there also you don't need to worry. Here we have the luminosity. The luminosity is scaled according to sun. So this is in the logarithmic unit. So this is log of luminosity of a star divided by the log of luminosity of the star divided by luminosity of the sun. And here we have the temperature. And this is basically the relationship between the two. And yeah, so you can see that this one. So this is the main sequence. And stars mostly spend their life in this main sequence. They burn hydrogen in the core. And if you go towards top right, you have red giants and red supergiants. So these are the stars which have very less temperature, but they are very luminous. So luminosity is basically 4 pi r square into sigma t to the power 4. So even they have temperature less, but the radius is very large, and hence the luminosity is large. And then on the top left you have blue supergiants and blue giants, and these ones are the white dwarfs. So they have a very high temperature, but they are dwarfs. That's why the radius is very small, and hence the luminosity is small. So next we have. Right, so yeah, we have the last point is important, that the stars are not lazy there, so they actually move around. So one thing you need to know. So this is the this is the main sequence branch. The star will go from the main sequence branch to the subgiant branch and the red giant branches, and eventually it comes to white dwarf. I have a different slide which will basically explain all of that. So we will leave that. And one more thing. Okay, one example. Let's say we have two stars, star A and star B. Star A is 10 solar mass and star B is 100 solar mass. Which of that star do you think has a shorter life?
100.
Why?
वो लाइट ज़्यादा एनर्जी यूज़ करेगा तो चलेगा.
Answer.
It will use more energy in less
Yeah,
time.
but it has less energy as well. So it has more energy as well, right?
Yeah, so it will use more energy. So it will.
It is actually fighting against the pressure that is happening due to gravity. So basically, a star is actually in an equilibrium due to radiation pressure and what gravity is trying to crush it. So there is this dynamic equilibrium which a star is always present. As the fusion proceeds and it reaches to the place where iron is formed after thermonuclear fusion, the gravity starts dominating.
So these are the relationships which you need to consider. The luminosity is mass to the power 4. And if you compare it with the fuel, so fuel is approximately mass to the power 1. Right. So since the luminosity increases by fourth the power encompasses one power. So because of that, the rate at which the energy is spent by the star will be more for a high mass star, and that's why it has a less light. Okay, so now, so stars form from nebula, from giant molecular clouds, all that. They become protostars. So protostar is basically a step before the star formation, where you do have an object which is congested. The gas matter is congested, but the energy at the core is not enough to start the thermonuclear reaction. And then depending on the mass, so a high mass star is basically any star which has a mass greater than 8 solar mass. A low mass star is the one with less than 8 solar mass. And this one becomes red supergiant after main sequence, that becomes red giant, then planetary nebula and white dwarf. This one, the high mass one, that goes through supernova. Supernova is one of the most energetic explosion in the universe in stellar astronomy. And then this either gets converted into a neutron star or a black hole. That depends on the core at the time of supernova explosion. So I will not be able to talk about black hole, neutron star, white hole because I don't know much about that. And that's why I have some suggestions for you regarding the YouTube videos. So this one is my first talk, and this basically covers everything in star formation and evolution. So I will also share the slides. I think the slides are self-explanatory. So if you just go through that, you will be able to understand it better. And then this one is by Mr. Prasad. He is one of the PhD student under Dr. Ritam Malik. And so this talk will talk about the compact stars. So compact stars are basically white dwarf, neutron star, and black hole. So if you want to know about that, you can go to this one. So yeah, so this was all about stellar evolution. Again, I know that it's not that clear, but I have alternate slide and which will make it more clear. So please wait for that. Now we will talk about star clusters. So, okay. So does anyone know why we should study star cluster? Like why should we care about the stars in a star cluster in comparison to stars anywhere around in the sky?
Because it's easy to locate a star cluster than a single.
Not exactly. If you can also look at the galaxy, right? Galaxy also has a lot.
We want to know how those stars formed very closely because the space is very vast, so most of the things are very far away. But the star clusters, such huge objects of the space, are very close together. So how did they form?
It's not related to formation. It's not related to how the star.
Their denses were more interesting things that are happening.
Well, that's one of the reasons why should we study a star cluster to look for exotic stellar populations which comes in the dense. But density is also there in many other places, right? Then why?
Then it's a star cluster.
It's basically this thing. So star cluster has family of stars which are at every stage of evolution. So, and that's the reason, that's the property, and that's the reason we need to study star cluster. So these three properties you need to consider here, and please remember that. First thing, all the stars in the star cluster they are at the same distance. So I don't need to calculate the distance of each and every star in the cluster. If I know that this star is a member of the cluster, I know what's the distance. I don't need to worry about it. And if you know that if we know the distance and if we have the apparent magnitude, we can know the absolute magnitude. From there we can know temperature. So that is one thing. Second is they move together in space. So since they all are gravitationally bounded with each other, so they move together in the space. This is very important when we want to find whether a star is a member of a cluster or not. About which we will go in the next one with the next slide. Then they are formed at the same time. There is a question mark there because I will probably show you at the end that no, this is not the case. Not all the stars in the cluster they are formed at the same time. We used to think, but there are some anomalies in that. But in a general case, all the stars formed at the same time. So now the question is, what is the thing then that differentiates the star from another star in a cluster?
The amount of heavier elements present
Yep.
in the star.
It's not about the amount of heavier elements, it's about the mass of the star. Because as I said, depending on the mass of the star, the evolution is faster or slow. And that makes a lot of difference. So now, this definition is a technical definition. And this is given by Cross. So they define this cluster as a group of stars inside a closed tidal surface, such that the group of stars should be gravitationally bound. Because if they are not gravitationally bound, then they are stellar associations. Does anyone know what stellar associations are? Have you looked at the Big Dipper? Big Dipper is
Yeah.
Yes. And there are constellations as well. Some of the stars in the constellations they appear to look okay, they are together, but they are actually not. They are not actually gravitationally bound. They are just apparently from us they look together, and those are called stellar associations. And that's why this is the first property, first requirement. Second is cluster volume is not dominated by dark matter. Do you know the reason why? Why shouldn't it be dominated by dark matter? Why? Why is it required for the cluster volume to be not dominated by dark matter? What happens if a group of stars is dominated by dark matter?
Because the stars will be affected by the presence of the gravity due to dark matter will interfere with the gravity of other stars in the cluster.
Not exactly. That's the definition of a galaxy. That's the definition of galaxy. There are some dwarf galaxies which have stars which are equivalent in the number of stars, equivalent to the number of stars in a star cluster. To differentiate between the two, you need that second property. And the third one is just a trivial property because there has to be some minimum number of stars so that we call it cluster. Otherwise, they can be called as multiple star systems like binary star and so on.
Excuse me. In the second point, you have said that we need this point to differentiate between dwarf galaxies and the star clusters. But there have been evidence of galaxies where there is a lack of dark matter also.
They have been galaxies. At least, like they are not confirmed or 100% sure about that. We think that they do not have diameter, but it's still going on. But also the extent of the expanse of those galaxies is huge as compared to these star clusters.
And the second thing is that now I think there are some studies where they have found some clusters which does have dark matter. So now it's all gray area. That's why I said there is a question mark there because
And
most of the
first
understanding
point.
is going on.
At the first point you said, at the same distance from us. Like, what does it exactly mean? The stars are equally separated or they are equally separated from us?
From us, if we consider on an astronomical scale, all of them are equal. Right. Okay. I need to follow up. So this is NGC 362. This is the globular cluster, and this is currently the last one. Because for last 2 years I have been working on this cluster, and this cluster has given me a lot of work. Right. So now I will answer the two questions together: type of clusters and why care about them. So this is open cluster, and PETs I think many of you have seen if you have attended the observation sessions. So now if you make a diagram, this is color, this is magnitude. Right now, just you don't need to worry about what is color, what is magnitude. Just consider, let's say this is some temperature scale which is increasing this way. Just imagine. And this is some magnitude scale which is increasing this way. Okay. So this one are more brighter and this one are more hot. Yeah. So now, if you make a HR diagram, it's a color-magnitude diagram, but I will say it's a HR diagram of these stars in the cluster. Here, you will get this. Does anyone know what is this line?
Means the all there will be different stars at different stage of evolution.
That's true. But what is this particular branch?
Main sequence.
This is main sequence. Acha, why only main sequence is there in the open cluster?
Because there are less giant stars in general.
No. So open clusters are relatively young, and as I said, stars spend most of their lifetime in the main sequence. So these stars do not get enough time to evolve from here to the higher stages. And yeah, so another thing about open cluster is that so in open cluster you have less than 10,000 stars around, and there's no proper shape, right? It can be very irregular. And apart from that, these stars are mostly found in the plane, in the disk, yeah, in the galactic plane. We'll come to that later. So इसको देख के मजा नहीं आया. Yeah.
Can you explain again what this graph is identifying?
So this is a magnitude. A magnitude is just another scale for brightness of the star or luminosity of the star. And this is the color, and color is just another scale for the temperature of the star. This is basically observational exotica. In observation, we just have the magnitudes in different ranges. We don't have the temperature of the luminosity. Okay? So इसको देखिए कुछ ज़्यादा मजा आया है. सिर्फ मेन सीक्वेंस ही है. So let's go to globular cluster. So this is globular cluster M3. This is one of the most studied globular clusters, and also it's one of the closest and one of the oldest as well. Not the closest, but the oldest. Now this one. Now you can see why we need to study star cluster. Why, and specifically globular cluster? Because just from the stars inside, you are able to study all different evolutionary stages. So this is main sequence, this is subgiant branch, this is red giant branch, AGB, this is asymptotic giant branch, horizontal branch, PAGD, you don't need to worry about. This part you need to remember this. Okay, this is BS. If you know the full form, that's fine. If you don't, we will come to that. This is not by. And now, so for the globular cluster, the number of stars are more than 10,000, and they are mostly found in the bulge of the galaxy, in the halo of the galaxy. And apart from that, yeah, so most of the stars are very old.
So this is the central bulge of the galaxy.
Yeah, around the bulge. I will come to that in the next slide. I will show you. Okay, so is the difference between the open cluster and globular cluster clear? Clear? And is the reason behind why we need to study globular cluster clear? It's just a package, okay. You have a single object, if you study it, you can study literally every evolutionary stage of the star.
What is the average distance between stars in these star clusters?
Actually, they are very far apart, right? And in the center, if I talk about in the terms of arcsec is basically the tip, right? So that is 0.5 arcsec, 0.2 as well. In the outer regions, you have the distance, like the minimum distance can be 1 arcsec, but it can range to very large numbers.
Globular structures are older.
Yeah, globular clusters are older. And it will be quite obvious from this one. So, yeah, so this is halo of the galaxy, and you can see the globular clusters there. They are also found in this bulge area because this one also has a lot of old stars. While these open clusters, they are usually found in the disk. And if you know, in the disk, the star formation. So that does make sense. Okay, the youngest clusters are there in the star formation. That does make sense. Alright, so this is about this one. You don't need to worry that much. Just that they are in the star formation region, and these are usually very older. They are in the bulge.
What is the galactic halo?
Answer.
Galactic halo.
So halo is the, so you have the galaxy. This is the disk of the galaxy, and then you have the halo region, in which is mostly composed of dark matter, and there are globular clusters there as well. And like what I believe is that it should be easier to study those clusters because they are not dominated by this.
What is KPC?
That's kiloparsec. That's just a unit of the distance. 1 parsec is 3.6 light years. 3.26 light years. So you can make the questions. Right. So this is about star cluster. clusters now.
I had a question. So, I don't know how much it relates to it all, but we have a galaxy, a halo, or you can say a dark matter halo for elliptical galaxy also, and for a spiral galaxy, just as you showed in the slide before. So, do we have any estimate about the number of globular clusters that we find in these two types
In
of
Milky Way galaxy, there are about 150 globular clusters. I don't know about the estimates on the other galaxies.
In general, I'm asking for a spiral and for an elliptical.
So I think for
dynamics are different.
elliptical, I can think of one thing, that the elliptical galaxies, most of the stars are old.
Yes.
And because of that, I think the open cluster should be less and there should be more number of globular clusters. I don't know the exact estimate because most of the clusters which we study are in the galaxy only. Because in the galaxy itself, we have 150 globular clusters. And as you move farther apart, you don't have that much of good photometric data, and it's not possible to study them in deep. So now this one. So I told you one property of the star cluster members, that they all move together in this space. So now, so whenever you are observing any particular patch of the sky, you have the stars which are in the cluster, you have the stars which are in the field as well. Field stars are basically those stars which are not the member of the cluster. Alright? How do we differentiate between the two? So one thing is using distance, but distance measurement is not that easy in the astronomic field. So what we can do is that we can measure the proper motion. So proper motion is what? So you know latitude and longitude, right? How many of you are not aware of RA index, right ascension and declination? So latitude and longitude is what we use for Earth. You all are aware of that at least, right?
Yeah.
So RA index is something which we use in the celestial sphere. So let's say I'm at Earth, all around me is the night sky. So let's imagine a sphere. Imagine a sphere, and all the stars, everything is projected on that. So this one is your declination. So this is plus 90 to minus 90, and then along this you have your right ascension, so which we measure as 0 to 24 hours. So 24 hours is equivalent to 360 degrees, and you can make the calculations accordingly. So let's say if you have a star here, so star is moving like this. So it has a component along this as well. It has a component along this as well. So this component will be proper motion in declination. This is proper motion in RA. This plot is basically just so these are various stars. So this is Gaia ADR3 data of the NGC 362 cluster. So what we do is that we make a plot between EM DEC and EMR, which is proper motion in R and proper motion in DEC. And as I said, if the stars are moving together in the space, they should coagulate together in this plot. But the problem with NGC 362 is that so NGC 362 is in the southern hemisphere. It's close to Lurkers constellation, and it's close to SMC as well. You guys are aware of SMC? Yeah, so that's one of the dwarf galaxy, right? So about this dwarf galaxy, what happens is that since there are two objects, see, galaxy also has a lot of stars, and the cluster also has a lot of stars. So it's very difficult to differentiate between the two because they both will form clusters here. Right? You have two coagulations. One of them is surely SMC, and other is the globular cluster NGC. But how will you find it? So what we do is that we color code these two clusters here. We make this plot. This is again the HR diagram plot. Sorry, the color magnitude diagram plot. And you can see that there is one which is clearly showing the pattern, which you have seen in the previous slides, and this is some random. So we definitely know that this is the cluster members, and these are the members of the galaxy. Is this clear?
Yes.
Any doubt here? Okay, very good. So now,
How was the data measured and represented in the graphs that you produced?
so this is the data from Gaia. Are you aware of the Gaia survey? So Gaia is basically a survey by ASO, which takes the data of all the stars in the Milky Way, and it's mostly used in the research field. It is mostly used for the astrometry. Astrometry is measuring the positions of different stars and how the stars are moving in the sky. Right. So what I have done here is that I have extracted those stars in that particular region where I know that okay, there is NGC 362. I made a plot between proportion theta and proportion Rn, which is provided in the Gaia survey itself. You make these two clusters, right? So I have these two stars, I have grouped them, and after that I make a plot of G versus dq minus rp, which is basically nothing but color and magnitude. We have two different clusters here, and we can see one pattern which is closely resembling to our evolutionary history chart, which I have shown you before. And this one is some random. So definitely I know that this should be the global cluster because we have discussed that before. Is it clear now?
What are the blue dots?
Oh, those are field stars. So there are some stars which are neither the part of the galaxy nor the globular cluster, but they are the stars which are in the field.
How were you able to differentiate among?
So field stars are very random. So since the field stars they are very random, so they will be all randomly distributed here. They won't be found in these ones.
Like, they also appear to be clustered.
How these blue stars are appeared in cluster?
Like, they are also the dots are representing the stars.
Yeah.
So like the many dots are close together. So you
Oh, this one you mean? Oh no. Actually, like I won't be able to show you here. So can you see the whitish? This is the
Yes.
So that is so. This is the property of this particular chart. This is density chart. So if it is more white, it's more dense. So even though you can see this one, the number of stars are very less in comparison to this one. And I forgot the percentage, but I think this will be only around 5% of the total number of stars. Right.
What are the yellow stars?
Yellow stars are the stars of the SMC galaxy.
So why don't they follow this particular thing? Because like all I think like all the globular clusters and the SMC should have like similar age. Like I expect SMCs to contain stars of all ages as well. Then why don't they follow a similar trend?
You mean that all the SMC stars are formed at the same time?
No, no, no. I expect like since it's a galaxy, it's a small galaxy. I expect that the like each star of like all of the ages would be present there. So if I try to plot an HR diagram, it should also give me something like that for the globular cluster because I also expect that all type of stars are present in a galaxy at least.
What is the age of SMC by the way?
Sorry?
What is the age of SMC?
I'm not sure. But it's very old. It's a satellite galaxy of the Milky Way, so it should be. It's older, like yeah.
It's older than Milky Way.
As well. But like yeah, since it's a satellite, I can expect that it should be the age of the globular clusters as well. So I can watch it.
I think the age of this globular cluster is around 11 gigahertz. 11, 10.5 gigahertz. So we can discuss that. But this one is clearly, so I have to discuss the why one, why question. But this plot clearly shows that okay, this of course cannot be the cluster. So this has to be the SMC because there is no other thing there which is coherent. So we can come to this. So these two videos. So I will talk about this one first. So unraveling the HR diagram. I will share the slides if you don't want to go to the video. But if you want to know about the color and magnitudes, which I am completely like every time I say color and magnitude, and there is some kind of ambiguity in what is color, what is magnitude. So you have to go through this. This slide will explain everything which is there in the HR diagram, from temperature, luminosity, magnitudes, color, as well as the spectral classes. And this one is about that. So this is about star clusters, and this is a complete overview of star clusters, the different types of globular, even different types of globular and open clusters. So that is something very new for me as well. So I want you to check it. Also, you explained about the dark matter in clusters as well. So yeah, if you want to look into that, this is the good one. And what else? Yeah. So one more thing I wanted to mention, I forgot. If you want to know more about this, that how we actually use this proper motion to get the cluster membership, you can talk to the other coordinator Niharika because she has done a similar project on this. Okay. So now, before we move to binary stars, can you switch off the lights? So I want to show you another slide which is not made by me. No, not all. I mean, just the point. Yeah. So I will actually prove right now that whatever I am talking about related to the diagram and everything, this is no box, this is reality. And I can show you from an actual image. So this is taken by, so this slide is made by J. Anderson. He is in STSI community, and I'm thankful to him to share the slides with me. So this is basically, so this is an image of Omega Center. Omega Center is one of the closest globular clusters and the largest in the kingdom, which is the factor of India. So yeah, this is the image of HST, and right. So you can see that there are different colors. There is red, green, and blue images.
Is this like deep into the heart of the cluster?
Yeah, this is actually deep into because HST has a very small field of view, and that's why you are seeing so many stars today. So the red image, so there are three different images which are combined. One is the red image, which is basically, okay, by red I don't mean that this image is of the wavelength red color, right? This is 814, which is almost in near infrared, and which we have color coded as red. Then you have the green image, which is 336, and 336 is around blue, maybe blue, I'm not sure. But what my point is that the wavelength is less, so these stars are of course having more temperature. So if there is a star which is brighter in a filter which is of a shorter wavelength, then it should have more temperature. Does that make sense to everyone? No. Yeah.
Didn't understand it.
So there is this Green's law, right? Lambda is proportional to 1 upon 10 to the power 4, right? Yeah. So if there is a shorter wavelength, the temperature should be more. Yeah. Now it makes sense. Then the last one is the blue image. This is 225 image. 225 is near UV. This is not blue. This is near UV. In HST filters term, we call it UV. Then what we did is that we combine all of that. Now I just want you to look at that. Right. So one thing is that look at this star. This star is appearing very bright in red, but as you are moving, it gets very faint. Right. So it doesn't necessarily because you know the diagram, the black body curve. Yeah. It peaks at only one particular value. Yeah. So if a star is very bright in one particular filter, it doesn't mean it should be bright in another. We combine all of this. What we do is that now we want to separate it out. So what we are doing is we are keeping the blue stars towards the left. We are keeping the red stars towards the right. Okay. So you can see that most of the stars are here. Basically, which means most of the stars are balanced, which are in the visible, neither in the infrared, neither in the UV. Now, what we will do is that we will also separate them in terms of their brightness. So, the more the bright the star is, it will be in the top. And then you get the HR diagram. The HR diagram of the colorimetric diagram. So, this is an actual image. These things actually happen.
White dwarfs and
Okay, so white dwarfs they are actually observed only in the UV wavelength. So they must be somewhere. Yeah. So okay, they are not visible in the screen, but they are somewhere. I will show you. There is a annotation of that. So this is called color magnitude diagram, and so they don't fall under this. This is the main sequence. In the main sequence, all the stars are burning hydrogen in the core. That's all. There's nothing else happening. There's just hydrogen burning which is going on. Hydrogen gets converted to helium. Okay? And also, you should not think, okay, there's a star here which is moving like this, then going like this. It's not like that. A star here cannot come here. It will go somewhere. So you don't. It's not that continuous. Okay, there's a star, then it's going like this. It doesn't happen that way. That's all this slide means. Then, of course, the more the massive star, it will consume more fuel. And then this is the subgiant branch. So what happens is that, see, eventually the hydrogen in the core, it will get converted to helium, and all this helium is getting deposited in the core itself. Now, you need to understand this thing. To burn helium to higher elements carbon, you need high temperature, which is not there in the low mass star when it is in the main sequence. So what happens because of that? Someone was talking about hydrostatic equilibrium. So what happens is that if there is not burning happening, if there is no nuclear reaction happening, there is no outward pressure, and because of that,
Gravity compresses.
so there will be contraction of the core, and so this is the place, the subgiant branch. This is where the contraction of the core happens. You can see that the luminosity is not increasing, but the temperature is slightly what? Is it decreasing or increasing?
Decreasing.
You just said there is no nuclear reaction happening, so how can the temperature will increase?
Oh, sorry, I was looking at the.
This you need to understand. This is this way. The temperature is increasing this way. The luminosity is increasing this way. This is inverse scale on the x-axis. So what happens is that after this star goes through the subgiant branch, there is enough of helium which is deposited in the core, and this contraction of this is actually increasing the temperature in the outward shells, like just out of the core. There is hydrogen, and that hydrogen will have enough temperature to get converted into helium. So now there is an inert helium core, but there is hydrogen burning which is going on in the shell which is just out of the core. And in this case, what happens? Since there is a hydrogen burning happening in the shell, there is increase in the temperature. What happens to gas when you increase the temperature? It expands. And if a star is expanding, what will happen? Temperature will decrease. What will happen? It will expand, so radius will increase, luminosity will
Decrease.
luminosity will
Decrease.
luminosity is equals to 4 pi r square into sigma t to the power 4. So if radius is increasing, luminosity is
Increasing.
Yep. So so it's moving towards this way. That means the temperature is decreasing, but the luminosity is increasing. This is the red giant branch. Now, after red giant branch, what happens is that even the shell burning stops, right? Because there is more and more which is helium. Helium is getting deposited in the core. The core is getting heavier. The core will contract, and there will be at some point the helium will have enough. So helium core will have enough temperature to ignite the thermonuclear reaction, which will convert helium to carbon. At that point, what happens? If there is an extra reaction happening, there is more energy, so the temperature will increase. That's where the horizontal branch comes. So along the horizontal branch, you can see the blue stars because they are very bright, right? And the temperature is increasing. After the horizontal branch, what happens? So the helium fuel is not as potent, means that the rate at which the helium fuel is consumed in the core is very fast. So whatever the process which are happening after this main sequence, they are very fast. Okay. So then helium, helium also in the core, it will get converted to carbon, and for a low mass star, we do not have enough temperature to get carbon converted to higher elements. So that's the end for the core. What happens after that? Even there is helium in the core which is getting converted into carbon, which cannot be converted into any higher element, but there is still helium which is there in the outer shell. That will get converted to carbon. That happens in the AGB, which is not shown here. So AGB is basically another kind of a asymptotic giant branch which goes along the red giant branch. After that, what happens? You have a carbon core which cannot be ignited to any higher element, and all the outer layers, the star becomes so large and it doesn't have that much of gravity. All the outer layers will just get emitted out in the form of stellar winds, and you have a core. The stellar winds may form a planetary and in the core you have a white dwarf. This is the evolution.
Is there any nuclear reaction occur in white dwarf? Is there any nuclear reaction occur in white dwarf?
No, so white dwarf are sustained by electron degeneracy pressure. So we can discuss them.
Can you go to the last?
Last slide.
You talked about the rapid jump from the RGB to HD. So why aren't there any stars in between? Do we not see or?
No, there are stars in between, but you have to understand this is just an observational pictures.
No, so observation we have not seen anything in between that region between RGB and HD.
So you have to understand the scale here is not exactly. It's made as an illustration. So of course there are stars between the two, right? There will be stars. Maybe they are not seen. But there are no stars. But there is one thing. The jump from RGB to HB is very fast. There is a process known as helium flash. So we can discuss that later. But that is something which is out of the scope of the current. Yeah.
You were talking about RGB, that luminosity is increasing here. And you talk about the so the formula is sigma pi r square T strip by 4. So it's T strip by 4 and temperature is decreasing. So that means radius is increasing much significantly. Is that right? Or
Yeah, correct. That's correct. Okay, so now we will move on to our talk.
Where will the HB come in this picture?
In that picture, that was not shown there, but let me see if in the previous one it's shown. It's not there. So it's not there in any of this HR diagram, but there are HR diagrams. I will okay, it's shown here. No? Yeah, this one. You can see. So this you can see this is asymptotic. I think first year mathematics course you know the asymptotic means. Asymptotic. So this is moving exactly parallel to RGB. That's why it's asymptotic channel. All right. So up till now, I just want you to know some of the things. Star, it starts in the main sequence. After main sequence, it goes to subgiant branch. Then RGB. That's all. Eventually, it gets converted to white dwarf. That is one point. Second point, the more the mass of the star, the less is this light. Okay. And the third thing is, the globular cluster, all the stars are formed at the same time. They move around the space together. They are gravitationally bound, and they are equidistant. That's all we want to do. Yeah. So now we move on to binary stars. So binary stars are couples which are orbiting around each other, but they are like twin bodies because they sometimes practice candles. Why they practice candles? How they do it? We will learn. So types of binary star systems. So there are different types of binary star systems. It's very easy to understand that. First of all, you have optical binary. Optical binary is some kind of binary which you can see from the eye. Okay, yeah, there is a binary. Example?
In the constellation, in the Ursa Major constellation,
Is that? Yep. That is an optical binary. Then you have a visual binary. So for visual binary, what you have is that you have an observation with time, and you can see that the other star is moving around. Do you know any example of such a binary? I'm not aware of that, but I trust you. Any known example?
it is actually tertiary. So there are 3 stars, not actually 2.
Okay. So there is Sirius as well. Sirius A, Sirius B. So for that also you can have observational picture that okay this is moving around it. So yep, that is that one. Then you have the eclipsing
I
binary.
understand the difference between optical and visual.
So visual is actually the binary which is actually a binary, while optical is the apparent binary. And then you have eclipsing binary. Eclipsing binary you also studied this in planets, the transit method. So and also eclipsing binaries are also called as photometric binaries, because what happens is that if there are two stars and if one is eclipsing the another, then you will have a dip in the brightness. Does that make sense? If there is a brighter source and another source is moving around it, it will obstruct the light, and that's basically the eclipsing binary. Sorry. After eclipsing binary are also known as photometric binaries because that's basically the photometric data you're getting. By the way, you guys are aware of the photometric data, what I mean by photometric data, right? No? Okay. So photometry is basically the science of measuring the brightness or luminosity or the flux from any object in the sky. So what we care is just about the brightness. It's just about how much the light you are getting from that particular object in a particular figure. That's photometry. Okay. So then you have astrometric binaries. Sirius is also an astrometric binary, by the way. So astrometric binaries, what happens is that since there is another star which is in the vicinity, which is orbiting, there is wobbling happening. Is it clear? You know the sun wobbles
around the center of mass of our solar system.
So it's the same way. So what happens is that there is a brighter star. Okay, we measure the proper motion of it for a very long time, and what we see is that this star is not following the curve, but it's actually wobbling around. So this is the astrometric binary, and I think Sirius is also an astrometric binary. Like it was like observed for a long time, and we have that data. Then we have spectroscopic binaries. Spectroscopic binaries are this one. So what happens is that so let's say if the star is orbiting around another one, you will have continuous U shift and red shift. So if you measure it for a long time, you will get okay, there's this U shifting happening on the lines, then there's red shifting happening, and there's only one reason for that. No star is moving like this or this. There has to be some star which is orbiting. You guys are aware of spectroscopy? Spectroscopy is the science of extracting spectra of any particular object in the sky. Okay? It's basically for any object, but since we only care about astronomy, so we will only talk about celestial objects. Then we have the sixth, which is the spectrum. So spectroscopic is just by the redshift or blue shift. Then what happens in the spectrum? And spectrum, in the spectrum, what happens is that see, you have an object which is very far away, which I cannot resolve. Okay, whether it's a binary or it's a single star system. So, but at least in the spectrum, what happens? You get the contribution from both the stars. Both the stars will contribute, and then the spectrum which you are getting is the combined spectrum. Now, the question might arise: okay, if we have how do we know if it's a combined spectrum, or if it's a spectrum from like two objects, or is it a single object? That's where the SED analysis comes up. Spectral analysis. We try to fit different models, and usually what happens in these cases is that you have a spectra, you try to fit a model of a single star, and you don't get a very satisfactory result, you get very high errors. Then you try to fit a binary fit. A binary fit is basically combining two different two spectra of different stars, and then sometimes that fits better. And if something fits better, that should be the case. And okay, yeah, I forgot to mention. Contact binaries are the most interesting ones because that's where the real stuff happens. And so these are the different things. Okay, you guys are aware of equipotential surface, at least in the terms of electricity. Yep. There are gravitational equipotential surfaces as well, and they are called Roche law. So this is basically the Roche law. So this one is basically a wide binary. Wide binary means none of these equipotential surfaces are actually interacting with each other. Then this is a transition between a semi-detached and a wide binary. Then this is a semi-detached binary. What does that mean? Is the material which is inside it, it's just there. So if it moves anywhere out of this, it will get transferred to this one. This is the place where the gravitational force which is observed by anything will be equivalent from both the systems. If there is any matter which is here, it will come in the vicinity of this one, I mean in the gravitational vicinity of this one, and it will get attracted to this one. And this is so this one is the closed binary system, but the rotation lobes are full. Like both the rotation lobes are full. So the matter can be transferred from each other. We don't need to worry about these ones because these are not interesting. And why they are not interesting? Because there is no mass transfer happening. So there are many things which happens in binary star evolution. Because there is a binary, because of that what happens is that sometimes the velocity of the other star is it's either increase or it's either decrease. The shape of the orbit it gets ellipsoid. Even the shape of the stars get ellipsoid. You know the example of Earth and Moon, like the tide and all. What I want to talk about
the last case.
it's a closed binary system.
And equipotential surfaces can't intersect each other, right? Because at that the electric field has to be perpendicular to the equipotential surface, and if they are intersecting, then there will be two directions.
Okay, I don't want that serious of an analogy between the two, but what I want to say is at this point, where are they intersecting?
That boundaries
No,
equipotential
these are
surface.
different. This is for this one. This is for this one. They are different sources. Different sources.
Just curious that double quotation at the end of points means something.
No, this is basically you don't have space to write binary also.
And aren't every binary system oscillating? So aren't every astrometric also?
But you have to observe it. Observation is
Those which are
for astrometric binaries you need first of all the long-term observation because you need to know the movement of this star. That's not possible in all the cases. We don't have that much of time.
Actually, all the six are the binary system, type of binary system, or the observation
You can say they are the type of binary system on the basis of how they are detected or how they are observed. Okay.
What is happening in the last case actually? Can you just elaborate?
This is a contact binary. This is actually this one. When the mass transfer is happening from one star to another.
Okay.
Right?
No, I was saying the E case, like the extreme right lobe.
This one.
Yeah.
This is basically a merger event. Like when both the stars are so close together that the matter is transferred between the two. So they both are in the same row. There is no different equipotential numbers for both of them.
Okay. So their centers have been merged, but they are still like they are.
Not exactly merged. This is a like stage before that. If it's merged, then you won't be having two, right?
Yeah.
It wasn't clear why you used equipotential surfaces.
I'm sorry, I didn't get it.
Why did you introduce equipotential surfaces? Yeah, I didn't get
The reason is that this is the equipotential surface for the gravity. At all this point, the gravitational force is the same. Okay. And here I have introduced this because the gravitational force here, which is from this one and from this one is the same. This is it.
So what does that plays the role in terms of the binary system?
Come to that in the next slide. So there are different things happening in the binary system. I want to talk about one particular phenomenon which is the mass transfer, which is kind of cannibalism because a star is actually taking the matter from the other star. So there are two different processes. There is Roche law overflow and then there is event equation. So we will come to this one first. Okay. Yeah, so the question related to the equipotential surfaces and why we have drawn it. So this is the equipotential surface. Okay. So yeah. So in the Roche law overflow, what happens? You have a massive star and then you have a low mass star. Okay. If a star is massive, it will evolve faster. What's the next step after main sequence? S subgiant and red giant. So this star will become red giant first, correct? And it will fulfill its Roche law. What happens if it fulfills its Roche law when there is some matter which is out of it? What happens? The other star, it can extract that matter. Why? Because at this particular point, the gravitational force which is observed, so gravitational force of this one is more. So the matter from this will get transferred to this one. Okay. What happens after that? So See, here you have rapid mass transfer because the equipotential surface, it already crossed the equipotential surface. But when eventually it will like there will be less matter and it will be in the equipotential surface, then the mass transfer will be less. What I want to show here is that if there are two stars, one of them is massive. The mass of it gets transferred to the other one, and the low mass star becomes a high mass star. Does that make sense? Yes. The low mass star, which was a red giant, and the matter is extracted. In the red giant, what happens? There is this hydrogen burning in the shell, and what's in the core? Helium, which is inert. There is nothing happening. So if I completely strip all the matter from the red giant except the core, we will have a helium core, and that helium core is helium core white core. So in such a system, this star will become a massive main sequence star, and the other star may become a white dwarf, helium white dwarf. Does that make sense? Okay. So this one only happens in the closed binary systems. It doesn't happen in white binary because of course the Roshanov will never get work. This case in which you can have this in the white binary as well as in the closed binary. What happens is that you have a massive OB star. OB is basically as O and B are spectral classes. OB stars are basically stars which have very high temperature and they are huge. So blue supergiants, blue giants. Okay? What happens? I told you that there is this stellar wind which is coming from the giant stars. If there is a compact object like black hole, which is far away, but still it has enough of gravity to extract all the. So what will happen is that the stellar wind which is coming, this will get transferred around black hole, and if there is stellar wind which is getting transferred around black hole, it will rotate. What will form? Accretion. Yeah, correct. We don't need to worry about wind accretion for our case right now. I just want to show you that there are two different processes through which the mass transfer can happen in a binary star system. Is this clear? Because this is relevant for the talk. So yeah, if you want to know more, so there is not much discussion in this talk related to the evolution of the binary stars, but this talk is more about the mathematical part of Roshanov. So if you want to know about Roshanov in more detail, you can look at this one. And I think the binary star system article is also there on the IBAC website, right? So you can also look into it. Okay, so after this, okay, do you have any question before we move on? So this is basically the last introductory part. After this, we will move on to the research experience. Up to now, do you guys understand mass transfer? How is it happening? Yeah. Do you guys know the consequences of mass transfer? That there is a low mass and high mass, low mass getting converted to a high mass star, and high mass getting converted to white dwarf. And you guys know the basics of clusters. Okay.
When there's white, the one which was smaller gets bigger, then there is the reverse process also.
Not exactly, because the other star is white dwarf then, right? And this star is a more massive star, but it still has a lot to cover. It has to become red giant, and so on.
When it becomes red giant, then the process goes back.
Okay, there is something related to that. Yeah, there are some evolutionary, there are some kinds of binaries in which what happens is that you get this one is getting stripped off, and then the other one is getting used, and then the matter is getting transferred. White dwarf has a upper limit, Chandrasekhar limit. You guys aware of that? So Chandrasekhar limit is basically the maximum hypothetical limit for any white dwarf to exist, 1.4 kilometers. But if there is extra matter which is getting transferred to it, it gets unstable. Right, and there is type 1 supernova which is happening. Very good. Type 1 supernova. So what happens is that white dwarf has a property that the more massive the white dwarf is, it is more contracted, it has a smaller radius. So there is a theoretical relationship from where the radius becomes 0 at 1.4 supernova, which is technically not possible. So that's why it's like that you cannot have a 1.4 solar mass white dwarf. And that's where this limit comes up. And what happens is that if there is a white dwarf, and you said that okay, if the reverse process happens, so that does happen. The other star, if it gets evolved, it becomes a red giant or whatever, and the mass is getting transferred. If the mass is too much, if there is more mass, and then because of that, if the 1.4 solar mass limit is there, which is there, it cannot sustain that. And if a star cannot sustain that, then there is this type 1 supernova which is happening. After that, type 1 supernova, this one gets white dwarf. So there are different cases which are based on the initial masses of the two stars, which I can explain maybe if I have time, because I have a paper on that. Maybe. So beyond the HR diagram, the reason behind the HR diagram is because these are the stars which basically contradicts our understanding of the basic stellar evolution. So the first one, I told you I will talk about this one, BSS or BS. The full form is blue stragglers or blue straggler stars, and these are rejuvenated stars. So the story goes back to 1953. So this is a color magnitude diagram, HR diagram, same thing of M3. Do you think this star should be here? I mean, according to our normal evolutionary history. Why? A star's in main sequence goes to SGB and RGB. Why are there stars? They are not supposed to be here, right? See, you know that these stars, if they are here, they are massive in comparison to this one. If they are massive, then they should have evolved to SGB or RGB. Then why they are here? These are the cluster members only. So they all are formed at the same time. And the stars of this mass should be here. They are here. Why? Try to understand this in the context of Roche-Low core flow evolution. What happened there? You had a high mass star, you had a low mass star. The high mass star evolved to RGB. It transferred its mass to low mass star. The low mass star becomes high mass star. Low mass star becomes high mass star. So this is basically that evolution which is happening here. Okay. So this was in 1953. Alan Sandage, he discovered that there are some stars which are brighter than newer than main sequence turn off. Okay, like this is where the star leaves the main sequence and goes to SGB. These stars are brighter and bluer than that one, and they are called blue stragglers. Straggler means lagging behind. The term was used because they somewhere are lagging behind in the evolution. They are not supposed to be here, they should be evolved here, but they are still. Why? Because there is mass transfer happening. With extra mass, you get extra life or extra rejuvenation kind of thing. So that is why they are called rejuvenative stars and all that. And this can only occur through some kind of process through which the mass is transferred. You guys know one process as of now, Roche-Low. There are two.
Doesn't mass transfer makes the evolution faster?
I'm sorry.
Increasing the mass makes the evolution faster.
It does. It does. But if there was a star here, okay, and if the mass is transferred to the star, that can come here.
Sorry, what did you say?
If there was a star here, which was in binary with a high mass star, which is now converted to RGB, red giant, even that is transferring its matter to it, then it will get evolved.
I mean, you said lagging behind the evolution cycle.
Yeah, it's lagging behind the evolution in the sense of the cluster evolution. Okay, so cluster evolution is basically like this. So this star should not be here, but they are still here. That's where the rejuvenation comes from. To understand that better,
Are you saying that they will follow it after some time?
Yeah.
So they are reaching it late.
Yep. And about that I will come in the next slide. Okay. So I have a image. So this was made by Dr. Snell South. She was an PhD in IISER. Now she is in some UK university doing postdoc. So this was these stars were first detected in M3 initially they were thought that okay, they are not the members of the family. I mean, they are not the members of the cluster, because if they were the members of the cluster, then they should not be there. That's what the initial assumption was. But then there were HST observations which confirmed that okay, they are members. But how they are members then? So how they can be like, if they can be young only if they have an extra fuel in terms of extra mass. How the mass can be transferred? You have the mass transfer process. Mass transfer process you all know, Roche know. The next process is collision. So if there, so see, if the globular cluster is very dense and there are many dynamical processes happening like mass segregation, two-body relaxation, etc., etc. Mass segregation is basically the massive stars are coming in the core and the low mass stars are moving out in the cluster. And two-body relaxation is basically, this is the, if there are two stars which are interacting with each other and all that, the velocity of the stars increases or decreases because of the gravitational interaction with other stars. And in such a dense environment, there might be events of collision which leads to mergers. Okay? These collisions can occur, these are not, okay, don't assume these collisions like this, not like that. Sometimes, like, no, not like that. There is just slight side of collision because of that also mass gets transferred. It's not always the merger. Merger does happen, but it's not always the case. And then this one is a proper merger. What happens is that I don't know this the mechanism that properly, but the idea is that there is a three-star system, and the outer binary, because of the outer binary, this inner binaries get closer. There is some tidal force which is happening. The outer binary moves away, like it leaves the multiple star system, and these two binaries they come closer and they finally merge. And of course, if they merge, then the final star will be of a higher mass, and that's how you get blue stragglers. So blue straggler is one of the mechanism through which you can. It's one of the exotic stellar population because, of course, this is something which is beyond the normal isolated stellar evolution, right? This is a different mechanism. Then, okay, this is blue lurker. This is a very new field. Okay. In fact, our research group in ARIES detected blue lurkers for the first time in Globular Cluster, in any Globular Cluster. So, BLs are like, okay, I don't think so. I should move to this slide first. Let's move to this one, and this will clear your doubt as well. Comparison. You have a BSS, and then you have a BL. So, see, there can be cases in which the mass is getting transferred to the star, but maybe the mass which is transferred is not enough that the star can outshine the main sequence turn off and come out in the BSS. That can be one case. Second case is maybe the equator star, means the star which is getting the mass is of a very low mass that even after the mass transfer it cannot come out of the main sequence turn off. That can be a case, right? That's where the blue lurkers come. So this blue lurker, compare. This is here and this is there before the mass transfer. Since it was here, after the mass transfer, it can outshine, it can come here. If there was a star which was here, deep beneath the main sequence, even after mass transfer, it won't be able to come here. But there is still a process of mass transfer which is happening, correct? Yeah. And that's why they are called lurkers. Lurking is hiding. So, yep. So this is the significance of that. So yeah, and I was talking about this one. So A is the donor star. The donor star, if it donates its material, it gets converted to white powder. So if I am detecting a BSS or if I am detecting a BL, what can be the possible companion? You know what companion is, right? Huh?
Companions.
Companion means, see, there was low mass star, there was high mass star, low mass star getting converted to BSS, then what happens to high mass star? The high mass star gets converted to white. So you get white dwarfs. You get hot short dwarfs as well, but usually you get white dwarfs with BSS. Does that make sense? But not all BSS will have white dwarfs. Does that also make sense? Because the white dwarfs will only be there if there is a Roche of overflow process. What if there was a merger? In merger you don't have white dwarf, you just have a single BSS. Okay? Does that make sense? Does the differentiation between blue and blue straggler is clear? Okay. Now the question is,
Blue lurkers are in the main.
They do have mass transfer, but they are still in the main sequence. Okay. Question is, how will you detect them? I mean, if I can easily detect this VSS, okay, they are here. But if there is a star which is inside this, how will you detect it?
We will try to find the other stars from which it.
And how will you find it?
There will be change in the colors.
We don't have the time for that. I mean, we don't have the time to look at the actual object and look for it. What we do is that we have three possible ways through which we do it. These are the three possible ways. First of all, just the text. These are post-mass transfer systems, just like VSS, but they do not appear brighter than the main sequence turn off. This could be due to lack of activated matter or due to a very low mass activated star. As a result, these stars have been designated as blue lurkers because they are the VSS type stars hiding in the main sequence. Alright, so these are the three possible mechanisms through which we can detect them. First is the multivalent acid analysis. Basically, you have the photometric data in various wavelengths. You try to fit a model, and as I said, if the single fit is not there, you go for binary fit. And what happens if you fit a binary in which one of the model you choose is the white dwarf and the other is the main sequence, and if you get the fit, what does that do? That you had a binary with the white dwarf and the main sequence, which is a clear sign of mass transfer. Then, second, so by the way, this is the method, observation of more than average V Sine. V Sine is basically the rotational velocity of the star. If a mass is transferred to a star, what happens to the rotational velocity? Will it increase or decrease?
It should increase.
Why?
Conservation of energy.
It's conservation of angular momentum with mass, the angular momentum conserved. Yeah. So because of that, the velocity increases. By the way, this was the method which was used for the first time to detect blue lurker. This was back in 2019, done by Emily Liner. She detected this blue lurker. So basically, she named this blue lurker, and she detected in the open cluster. Then this one, third one, I haven't read any publication related to this that they have detected blue lurker using this, but this can be a sign of mass transfer. Because see, if there's a mass transfer happening, there might be chemical peculiarities associated with it. Because let's say if it's a collision, in collision what happens? The matter which is there in the outer layer, it gets transferred. That is of different origin because that is of different evolution stage. Even in normal PSS type binary systems, the mass is transferred from a red giant, so the atmosphere is different, and because of that, there can be chemical peculiarities which are associated with it. Okay, so this is blue lurker. We had bush lurker. Blue lurker. First one.
First point to detect them.
Okay. The multivalent acid analysis. Can you do it like basically that will come later. So I mean it will be more clear when I will go to the research experience part. Okay. Your question. What happens to this BSS? So this BSS gets evolved to YSS. Okay. So YSS are basically nothing but the evolved BSS. So of course, see this will follow this one, then this will follow this one. We will always be above this. Okay. Characteristic of YSS, they will be above SGB and to the left of RGB. Above SGB, left of RGB. Okay. YSS, yellow stragglers. Now, beyond universe age. Why? Okay, I told you one thing that if there is a star which is of low mass, the evolution of it has a very it has a longer life. Okay, so the universe age limits the mass of white dwarf to 0.4 solar mass. What does that mean? See, a low mass white dwarf will come from a low mass star. That makes sense. And if there is a low mass star, there has to be a lower limit on that. That okay, चलो इतना होगा lower और यही evolve होके white dwarf बन पाएगा. And that is the 0.4 solar mass limit. Okay, so if you see here, look at this curve, single and white binary curve. All of this ends at more than 0.5. This is a graph between white dwarf mass and the primordial mass. Primordial mass is the mass of the main sequence star which is getting converted to white dwarf. So you can see that this is limited to, this is like greater than 0.5. We do not have the stars less than that in single and wide binaries. Why? Because the universe age limits the mass of the white dwarf which is formed by an isolated star collision. There is a minimum limit which is 0.4. What does that mean? We should not have any star, any white dwarf which is less than 0.4 if it was all isolated star collision. But yeah, that's the fact about stars. Actually, we usually think that they are isolated, but they are almost like 1/3 to 50% to 60% of the stars in the universe are binaries or in multiple star systems. And what happens? I told you one more thing, that in the mass in this binary systems there is the mass transfer happening, and because of the mass transfer, what happens is that the evolution of the low mass star is also getting facilitated. I mean, if you are stripping away the matter from a star, what is the matter? The core, which is the white dwarf. And if you are stripping that during the red giant phase itself, what happens? You actually accelerated the process by which the white dwarf forms. Okay, if it was isolated, RGB, sorry, SGB पे जाओ, फिर वहाँ से RGB, HB, and then white dwarf. But if there was a star which was at RGB and you are stripping away the matter from it, it gets directly converted to white dwarf. So you have increased the speed of the process. Because of that, you get white dwarfs which are less than 0.4 solar mass. Those are called low mass white dwarfs. And PLM white dwarfs are extremely low mass. And they are helium core. Why they are helium core?
Hydrogen core.
They are in the red giant phase. So red giant phase में क्या होगा? Helium core white dwarf है. Helium core ही रहेगा. बाकी आगे जो पूरा था वो तो strip away हो गया. That's why helium core white dwarf. And yeah, that's all. And they can only be explained by the mass loss which is happening in the binary system. Okay. And this graph actually shows that this is basically a model. So high mass star they get equal to oxygen and neon. So that's why you have oxygen neon core white dwarfs. Carbon oxygen white dwarfs are for those normal isolated low mass star evolution that forms carbon oxygen white dwarfs, because carbon is inert and that stays in the core. Helium white dwarfs, they are formed in close binaries mostly, and yeah, they can be in this range, the less than 0.2. This is the final object of the exotic star population that I wanted to talk about. Any question?
I didn't understand why this beyond universe age.
Beyond universe age is that basically if you find a white dwarf which is less than 0.4, it should not be there theoretically if you just consider the isolated white dwarf, isolated stellar evolution theory. Okay. Okay. But the thing is, there are many more exotic stars like cataclysmic variables, millisecond pulsars, active binaries, etc., 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 which I cannot talk about in this talk. But fortunately, my supervisor in view of it, he has given a talk on exotic binaries in globular clusters, and he has talked about all the possible X-ray binaries which can be found in globular clusters. If there is someone who is interested in X-ray astronomy, specifically in stellar evolution, specifically in stars, this is the talk to look for, because this talk has basically all the information related to the current research scenario which is happening in the stellar physics, in the X-ray specifically. Okay. So now I will be talking about my research experience at ARIES Nainital. So this was a publication in MNRS Letters this year, and so this is the PhD student with whom I work. This is my supervisor here. This is me, and these are the PhD students in IRA. She is the director of IRA. Yeah, that's all. And so now, so this one is basically about the first time detection of blue lurkers in a globular cluster, and which we did with the multivalent acid analysis, about which I will come in the further slides. So first of all, so what my objective was that I need to determine the properties such as temperature, surface gravity, radius, mass, etc. from the acid analysis and from isochrones. And what we have done is that we have used the data. So, okay, one thing. A star in main sequence will be visible mostly in which window? In which particular window? A star which is in the main sequence should be visible in mostly in which particular wavelength? In yellow color. Which is visible. Okay. A star which is a white ball should be visible in which ultraviolet.
Near.
Okay. Ultraviolet, near ultraviolet. So if there is a star, if there is not a star, if there is an object which is in the main sequence, which is visible in the which is seen in the visible image as well, in the ultraviolet as well. What does that mean?
It can be a very bright star.
It was then part of the binary system, but
It was a part of that binary system. So there, what we are seeing is a single star is basically a binary in which the white dwarf is giving a signature in the UV, and the optical, or the main sequence one is giving the signature in the visible. That's why we go to multi-wavelength astronomy. So we use the data from UVIT and UVOT. These are the corresponding wavelengths. So UVIT, these two filters are very important because they are in the far UV, and all these filters are in the near UV. Then you have these filters from ESO, NPI 2.2 meter telescope, which are basically your normal visible filters. Okay. The data was used from these ones, and Gaia, again, as I showed you in some of the previous slides, that Gaia is actually used to find the cluster members. Now, okay, so what do you do? As I said, I need to look for those stars which are observed both in UV and in optical, and they are in the main sequence. For that, what we did is that so this is basically this particular one. We have divided that into different sections and we looked for those stars in this one, which also have detection in UV. Okay. For that, what you do? You have two images. One is of UV, one is of optical, and you have the position of the stars in both of them. You cross match them. When you cross match them, you will find those stars which are observed in both UV and optical. And those are the stars which are interesting. Okay. So basically those stars which are here in the main sequence and they have UV detection, those are the stars worth looking for. Okay. So yeah, that's the thing. We look for them in the someone was talking about the distance. Like what's the average distance between the stars. So see, this one was only related to the outer region. We didn't look into the inner region of the cluster. We just looked in the outer region. Outer region is less dense. So 1.5 arcsec distance is okay. Okay. And then what we do is that we look for authenticity of this detection. See, no algorithm is completely correct. So even though if you have these are objects, they have UV detection, but I cannot trust that. You have to look into the images and see if the star is actually there or if it's just an artifact. An artifact can be a galaxy, can be a cosmic ray, or sometimes what happens, see the ESO, this data, it has chips. So there are different squares, CCD squares, and between that you have no observation, you have black, and sometimes a star comes in that. We found many stars which were very interesting, but they are in that black, and we have to straight away scrap because we cannot use them. The photometry is not authentic for that. Finally, you convert this data to AV magnetic system, then you convert this to flux, and then you do acid analysis, and so yeah, I will come to this. So these were the four blue lurkers which we have detected. This is the optical CMD. You can see that they all are in the main sequence. The position where they should be. And okay, this is basically a UV one. This is basically used just to look whether they are they have a UV detection or not. Okay, this one is not that important. What I want to show you is the positions. The positions, they are important. They are around the optimal positions for blue lurkers. So this is the first hint that they may be blue lurkers. First. Now, analysis. So, see, the point is, why do we need acid analysis from photometric data? To obtain a spectra, trust me, it's very difficult. It's very difficult to get spectra for stars, specifically in high resolution. And that's why you need this photometric data points. If I have multivariate data points, then I can use that to make the interpolated spectrum. Okay?
Why is it tough? Why is it tough?
To get spectra, high resolution spectra. To get high resolution spectra, first of all, see, to get the spectra, the observation time is more.
The observation time is good.
Yeah. Secondly, the resolution. Photometric data can be easily resolved, but to get highly resolved spectra for each and every star is tough. We don't have that much number of the spectra.
In a cluster or in general?
In general. You use SDSS almost, but they are low resolution. You don't have the high resolution spectra a lot. While photometric data is easily available everywhere, so you can use it. So, okay, so now here, these are the different photometric data points. These are, I think the optical ones. Then these two are the far UV ones from UIT. UIT is astrophysics, by the way, and it's highly recognized. It's one of the best far UV telescopes. And then you have UIT Europe. What happens? So this you have two different models here. You can see this is the gray one, right? And then there's another one, the blue one. Okay, can you see? So the blue one is the Coaster model. Coaster model is the white box model. And then we have this gray one, which is the Cruise model. Cruise model is basically a main sequence model. What you do is that you combine the curves of both of them. When you combine them, and if you get the fit here. Okay, someone was talking about multivariate ACD. Like how do we use multivariate ACD to detect the lurkers, right? So this is how we do it. So we have a photometric data point. We try to fit the spectra. We have used two different models. There is white box model, and then there is a Western model. You add the two, and if that is actually correlating with your observed data points, then you got the correct spectrum. You got the correct fitting, and with fitting, you get all the temperature, surface gravity, etc. And that's what WOSA do. WOSA is just a tool which does.
What does correct fitting means?
Correct fitting means this thing. The chi-square value. Chi-square value. You are aware of that? Error. Basically error. You look for the error between the observed points and your spectrum. Okay. And in this you can see the errors. Okay. So this is basically I think delta f by f. And you can see that error is in this line for most of the cases, and this is what we need. So there are some parameters which I probably haven't shown here. So there are particular optimal values for, so there is chi-square, then there is VGF, VGPF. VGPF and VGF are basically goodness of fit, which are measure of chi-square only. So there are some optimal values. If you are getting the spectra in those optimal values, that means okay, you are going in the right direction. So we do this, we get the modeling done, and we use WOSA. So WOSA, what it does is that it has this photometric models of both of them, and then it combines them. So F, which is the total flux, is M1 F1 plus M2 F2, where M1 and M1 and M2 are R by T square. So R is the radius of the star. Okay, so your total flux is M1 F1 plus M2 F2, where M1 is R1 by D square, where R1 is the radius of star 1. Okay, and D is the same for both of them because both of them are cluster members, so distance is same. You make that and you get these parameters. Okay. So A and B, 1551 is the object and this is A and B. So object A and object B basically are the two stars in the white dwarf. Okay. Some discussions which will confirm okay they are lurkers. So let's just discuss that. First of all, you know that their positions were near to the main sequence or not. I have shown you in the previous color magnetic diagram. They were near that. Second thing, the turn of mass is 0.8 solar mass for this cluster. The masses we got for these stars are 0.92, 0.85, 0.87, 0.80. All of them are close to the turn of mass, which is 0.8. This is the second point towards why they are lurkers. Then also, if you look here, then all the masses here 0.2, 0.18, 0.18, 0.2 masses of the white dwarf, they all are less than 0.4. What does that mean? That they are the result of mass transfer, which should happen. And then also, if you okay, I think it's not here. Okay, yeah, it's here. What's the age of this cluster? 11 gigayears. Okay. What are the ages of our stars which we found? 5.5 gigayears, 1 gigayear, sorry, 10 gigayear, 8 gigayear, 5.5 gigayear. All of those values are less than the 11 gigayear, which is the age of the cluster. What does that mean? That these stars are actually appearing to be younger than the cluster members, rejuvenated stars. Then what else? Yeah, that's all. Case A or B is basically, so case A mass transfer is when the donor star is in the main sequence, and case B mass transfer is when the donor star is in the subgiant or RGB branch. No need to worry about this right now. This is okay. Okay. So what happens? You get the luminosity and temperature from the HED fitting. You use that to plot a HR diagram, Hertzsprung-Russell diagram. Then what happens? You use isochrones. So isochrones are basically theoretical evolutionary tracks for stars. So all these are isochrones of different ages. Okay. So at whatever the point you get the star, you know at which isochrone it is, and isochrone will give you the age of the star. So age of the star. Yeah. And it's basically a scatter plot. So you have different points here. It's not continuous. And at each point you have the mass of the star. So from the theoretical model, you get the age and mass of the stars. The same thing happens with the white dwarfs as well. You have the isochrones for that, and you get the age and mass from them. Is this part clear? And now this is, by the way, this is the far away image of this cluster, and you can see these four objects. Okay, all of them are not in the cluster center; they are in the outer region, and you can clearly see okay, all of them are integrated in the unit. That's what we want. What else we have? So, yep. So conclusion. So we have detected for the first time blue lurkers in a globular cluster, and based on our HED analysis, we can say that these two of them have low mass helium white dwarf as the companion, and two of them has ELM, which is actually low mass white dwarf as the companion. One thing is that you can why they are formed actually, why they are formed in the outer region. So what can be one of the theories? So one of the theories is that there is a core collapse which happened recently in this cluster. And how do we know that? We can discuss it later if somebody wants to know. So because of this core collapse, what happens is that the density increases at the core. What we are proposing is that these stars maybe are formed during the core collapse and were expelled after the core collapse, they were expelled outside. And yeah, so this is one of the theory of their form. There can be multiple, but this is what we have proposed. And yep, so those of you who know the next question, because you have attended any of my previous talk, please don't answer. Please don't share with us. Yep. So, okay. So, okay, let me explain the question. So, when the stars are formed from the clouds, which are mostly composed of hydrogen, they get converted to heavier and heavier elements. Eventually, you get a supernova. After that, you get neutron star maybe. Okay, so from proton, you get neutron star, which is mostly composed of what? Neutrons. You know the binary, sorry, binary, not binary, binding energy curve.
Yes.
So what happens is for a stable reaction, your initial product should have a lesser or more binding energy.
Yes, sir.
Lesser, and the final one should have more. Okay. In this case, the proton has more binding energy, and it gets converted to neutron, which has a less binding energy. And we know that during the lifetime of those stars, they emit a lot of energy in terms of supernova, in terms of sunlight. How does that energy come from? That's the question. You had a star, you had an element which is proton, which is of high binding energy. It's get converted to neutron star, which is neutron, which is of low binding energy. How is that possible? This is not possible.
Is there binding energy for protons?
Yeah.
How is that defined?
How is that defined? Binding energy of hydrogen is defined.
Binding energy of hydrogen is defined.
It might be due to the
I mean, what is a proton? Proton is basically hydrogen nucleus. Binding energy is defined, right?
Like, what are we talking about? Are we talking about the internal binding energies of the proton or what?
Just understand this question basically. Can you turn on the light? Where is it? Okay. What my point is that initially the star was mostly comprised of proton, which has higher binding energy. Okay, and at the end stage is neutron star, which has a low binding energy. This process is not allowed, correct? And this is actually happening here. You have a lot of energy which is emitted, and still you are getting a product which is of low binding energy, which is impossible. So there has to be something which is happening. Who paid that to them?
Gravitational potential energy.
Bingo. It's the gravity. The gravitational potential energy of the final neutron star is much greater negatively. That's that. And yeah, the ultimate energy source in the star which produces the greatest amount of energy is gravity power, and this is an important